All right. So let's talk about what kind of big overview, what we're going to do with medical imaging. To do this, we want to get to the idea of what are the different modalities that we're going to cover. But I want you to think of it not necessarily just as the modalities, but how the image is being taken. Right? But let's start off. What type of medical imaging techniques are you familiar with? Just list any ones we've got.
X-ray.
Okay.
Off of X-ray, you got CT, MRI.
Okay.
Did you make it full screen?
Is that? Okay. That's great. All right. X-ray, CT, MRI, anything else?
Ultrasound.
Ultrasound.
That's all I've got. I think I can think of some more. No, like angiograms, but still like X-ray, stuff like that.
So there's some other ones just like CT. So right, so we could have an angio off it, right? There's some other ones that are kind of off the X-ray family, right? You could also say, for instance, like fluoroscopy.
Yeah.
Is another type of X-ray. We'll talk about what each one of these are. But let's just kind of get a few ones out there, right? So there's a few ones that are kind of like that. MRI, and in addition to basic MRIs, there's also what's called fMRIs. There's several different types of ultrasounds, but there's a few other techniques that we haven't even talked about or been mentioned here. Right here are PET scans. There's another related one to this, which is SPECT. I've mentioned on my own, there's proton CT stuff. That's a newer modality that's coming out. We've also got different ways to image the body using other types of techniques, so optical techniques that are out there. All right, so you might have even heard of like thermographs. This is kind of a mid-infrared one, right? We've got near-infrared spectroscopy, NIRS, which is kind of related to our areas of like a pulse oximeter. All right, so there's a lot of different techniques that are down here.
Is that what they were using on like the James Webb telescope to like take measurements, the near infrared?
So it's related.
Okay.
But a NIRS one, so this is where it'll get a little bit different. James Webb and all those are passive.
Okay.
So you've got an emission one out there, and you just need a receiver with a focus on it. For our case, if you're doing a thermograph, that's actually very similar.
Okay.
Right? Because the body is the emitter. And you basically, based on your temperature, right, what's called black body radiation, right? You're the non-visible spectrum. And there's a lot more radiation your body puts off in the infrared spectrum than it does on the higher range ones. Right? In theory, you can be putting off almost anything, but the rate becomes so small as to the likelihood of you emitting a photon of really high energy in 1,000 years is ridiculously tiny, right? Whereas with infrared, you're going to be putting off a lot. Right? So, thermographs are kind of measuring that one in a particular range. So those ones are often used for looking at the body to find out if there's, particularly hot or cold areas. You can see blood flow patterns, things of that sort. Whereas NIRS, we both emit and receive.
Okay.
All right, so we'll put in both combinations. And then the photons in the infrared will go through. Very often NIRS is used for measuring on the brain. You can use it for other areas. It also looks, the photons will only travel about maybe 5 inches or so. So NIRS is very heavily used for surface thinking on the brain. It's deep enough to get to your gray matter, maybe a tiny bit of white matter, but not much. But it's enough to get to the gray matter, which is where a lot of your thought process happens. So it allows us to see blood flow in those regions, which therefore will correlate to what your thinking is.
Okay.
So we can actually measure your thoughts by seeing how much blood is in different areas of your brain. Right? Your thinking areas are going to have more blood flow. And you can just watch because they're going to demand oxygen. So when you're thinking in a particular area, it'll open up the blood flow to that, try to increase. So you watch the total volume of blood will increase and things like that. And NIRS, it's related to pulse oximeters, which measure your oxygen amount. But they also measure how much, both oxy and deoxyhemoglobin you have. So then you also have total hemoglobin, so you can find pooling blood and all kinds of other stuff. Right. So NIRS is a good way to be able to measure brain thoughts and things of that sort. There are other ones that are related to that one, like for instance, you might not even think of, like an EEG. Right, we can get an image of your brain, at least on the thought levels. What's the electric pulses that's in there? Now, that's not an image in the normal sense of what you would do, but we do actually get a 3D reconstruction of where your thoughts are coming from and what type of pattern wave they're generating, which will tell you the type of thinking that you're doing. And EEGs are very nicely analyzed using frequencies. And so based on what your frequency is, we can tell how intense or what type of thought you have. If your thoughts are, for instance, below about, let's say 6 to 8 hertz, you're falling asleep. If it's below 6 hertz, say like 4 hertz or so, you are nicely asleep. If you're, say, in that kind of 12 hertz range, you're mellow, just thinking kind of cool, relaxed thoughts. As you get into higher, you get to the high teens, up to, say, like 50, right? The higher the number, the more intense your thought. So we can actually do a frequency analysis of an EEG and tell how seriously you're thinking on things just by doing a frequency analysis. So this is where a lot of your signal processing actually comes in handy, because breaking out the frequency bands will kind of tell us if you're above 26 hertz, you are spending some pretty intense thoughts on here. Whereas if you're in the 8 to 12 range, that's your theta band, and you're kind of, it's the mellow, drowsy thoughts. So a good frequency analysis will tell you everything you need to know off of those areas. Like I said, we can get them down to very precise locations. So, those ones are very specific ones. But if you think about it, EEG, your body is the emitter. We're going to put an array of detectors in different locations, and we'll use it to backtrack and find out where the thoughts came from. And then we'll use frequency analysis and other things to figure out how to look at it. That same idea we're going to do with almost all of these. And what you need to break down to say is it an emitter? Am I the emitter? So let's consider one of the basic ones. You guys right off the bat had x-rays. So I'm going to say you're probably fairly familiar with x-rays. What's an x-ray then? How does it work?
It emits radiation
Okay.
that
What type of radiation?
to your body. It's
Yeah. I mean, obviously it's x-rays, right?
Yeah,
But,
that's what it's like.
But what makes x-rays special to us? Are they high energy, low energy?
Are they lower? Are they low energy?
So here's the great question: what do we compare high or low to? Right? Because you can always, I mean, technically speaking, there's always something higher energy.
Right, right.
So it's a relative term when we say high or low. So what do we care about for medical? Have you ever heard the terms ionizing or non-ionizing?
Yes.
That's the breakpoint. That's what we compare everything to. Ionizing radiation. This is the important breakpoint for us. So right that breakpoint is 13.6 electron volts. That's the magic number. Right? If it's bigger than that, then it's ionizing. If it's smaller, then it's non-ionizing. So, anybody got an idea what 13.6 electron volts, what that means? Right? Because right now it's just an arbitrary number, right? You're walking down the street, how would you recognize 13.6 electron volts? Right? When they did physics or chemistry, did they talk about electron volts and how you have to ionize atoms?
Mm-hmm.
They talked about it, but they didn't really give us a scale of like what it means.
So let's get a scale, right? So what does it mean to ionize something?
To excite the molecule to a point at which it releases an ion, so it gains or loses an electron, right?
So it loses. In our case, it's always losing. What you're doing is you're adding energy, and as you add energy, so there's bands. So you have your nucleus, and around this, you have bands. And I'm doing this planetary model just for simplicity, right? Realize there is no such thing as a circular orbit in an electron. No matter what happens, electrons do not move in circular paths around an atom, ever. Right? And the reason I can say that, so even if you have a spherical orbit, they don't travel spherically. Electrons that move, that are in a charged field, that follow a bent path, emit a radiation and lose energy. So if the electrons around your atom the nucleus is a charge, so it creates a charged field. If that electron ever moved in a curved path, it would lose energy and it would fall out of that shell. But quantum says it's stuck in certain shells, so it can't be emitting that, which means it can't be traveling in a curved path. All right, so this is what's kind of weird to most people. The electron just fuzzes out into the shape of that orbital and then appears certain places and moves a short distance and fuzzes out. So it travels in short paths, and it fuzzes and collapses, right? But it never actually orbits around it in a normal sense. But it's prettier to draw it this way. So if you think, these are certain ratings of energy, right? For a typical, nucleus, if it's got, let's say, 2 charged particles, then there are 2 locations for electrons to go. And if you go past that to the 3rd location, then it's considered off your particular atom because anybody else can grab it, right? If it's out there, there's not enough binding it to that atom to hold it. So what you need to do is promote it to that highest shell, right? That's what's called the conduction band. So once it gets out there, it's free to move about the country. Now, a hydrogen only has 1 proton, so there's only 2 shells we care about. The one the electron lives in, and the next one up, right, which allows that electron to now move freely. The necessary energy to remove a particle from a hydrogen atom for moving an electron is 13.6 electron volts.
Mm-hmm.
Now, if you think of even the name of that, electron volts, right? How many volts apply to an electron?
Mm-hmm.
So it's even suggesting to you, right? A volt is giving you a potential field charge on a charged particle to move it someplace. So we're literally saying 13.6 volts applied on that electron will bring it away from a hydrogen atom, and you just get a free proton out of it. Does that make sense? That is that important standard. Now, the photon that has that much energy is ultraviolet light. Now, here's the important thing. What does ultraviolet light do to you that other bands of light below it, right? Blues, reds, infrared, right? Those are the lower ones, right? What can ultraviolet light do to you that regular colored light or infrared cannot do to you? Radio waves, things of that sort.
They can cause free radicals to build up in your cells.
Yeah.
Which,
And the most obvious one happens just in the summer is
Sunburns.
sunburn.
Yeah.
It's ultraviolet that's dangerous. Why is ultraviolet dangerous? It's ionizing radiation, right? Because those free radicals you're talking about, why are they free radicals? They're radicals because they've lost electrons. Why did they lose electrons? What's the most common atom in your body?
hydrogen.
Hydrogen, by far,
Yeah.
right? So you get, an ion of hydrogen, it's going to bond someplace, probably not where you want, and it can break something else apart, causing molecules to separate, right? So you don't want this charged particle just floating around inside your body because you don't know what it's going to bump into and bond with and break other things apart. So that's why we don't like it. Right? And that is the lowest level at which you have now created something that's going to create those free radicals that will now create dangers within your body, which can lead to cancer and all kinds of other problems of that sort. So if you have a non-ionizing radiation, you literally cannot ionize something, which means it's not going to cause the dangers associated with ionizing radiation. Right, so you hear people freaking about, all the radio waves passing through my head. Radio waves are significantly less energy than ultraviolet. They cannot possibly ionize anything.
Mhm.
So they can't possibly damage you in that way. Right? But basically you'll think of these as ionizing is potentially dangerous and non-ionizing is basically completely safe for the most part. There are some side effects that can happen from other things, like ultrasound is not ionizing, but if you do enough ultrasound, you can actually cause damage with that too. Yeah. Heat buildup and some other ones, which repeatedly doing it. Like some people hear it's safe, and so people buy a home ultrasound kit and watch their baby all the time, and that's not a good idea.
Yeah.
It's not dangerous because of the ionizing part. It's now dangerous because of other effects that are coming in. So it's an important caveat. It's safe unless you become an excessive crazy person. All right. Does that make sense on that kind of separator that's there?
Yeah, it does.
All right. And hopefully that gives you a good thing. So when you're thinking about that 13.6 volts, think ultraviolet and think hydrogen. Okay. So that's that basic separator for us. So on all of these, like let's see, what do we think about X-rays? Ionizing, non-ionizing. More or less energy than ultraviolet.
I'm gonna go ionizing.
It's safely beyond ultraviolet. Right? So it is definitely in that danger zone. It's nowhere near as much as like a gamma ray or thing of that sort, but it is way beyond ultraviolet.
The X-ray tube's the one creating that like ionizing.
Yes.
Okay.
And we'll actually talk about how to build an X-ray tube.
So I watched this guy on YouTube. He found like a really old X-ray tube, and he like made an X-ray in his garage. And he was like scanning his hand and stuff.
Oh yeah, you can.
Yeah.
And depending on how much you're outputting and things like that, you don't want to do an awful lot of that.
Yeah. Yeah.
But depending on which one it is, usually what you do, and like I said, we'll get more into this, but it's typically a tungsten element.
Mhm.
And then all you do is you get an electron accelerator, so you basically, like old TV tubes would do this. They had a big piece of glass to absorb it at the end. But if inside the vacuum you generate an electron, you accelerate them, and you have those electrons hit the tungsten. And when it does, it'll emit high energy X-ray that comes off. And it comes off at a known angle, depending on the angle you came in on, and it basically produces these. And then to do it systematically, we usually spin it to get even wear, so things come off in predictable directions. But yeah, at the end of this, you'll know enough to build that in your own garage, but you'll also know it's probably not a good idea to do that for any long period of time. Too much radiation, and even the rate at which the radiation is added will impact you. Right? So there's some weird effects that kind of take place, flash, things of that sort. It turns out really short duration, high radiation doses actually will not affect you very bad if they're above a certain threshold. It sounds weird, but you get, mid-range stuff, it'll kill you. You get to really, really crazy high, really short duration stuff, and it just doesn't seem to bug you at all. But there's limits to this, but there is actually kind of some oddball region that's in there, and that's one of those kind of hot topics right now. So, we've been talking a little bit about these. How about some of the differences that's going in here? Like, what is a basic X-ray? How does an X-ray work? All right, so we said we get like a tungsten or some other, metal that's pretty heavy. The reason why is actually those electron shells, because we excite them, and then we want to get a transition in the proper range. So we talked about the transition range for hydrogen is 13.6 from outside to in. So if an electron falls in, you'll get a photon of 13.6, which is an ultraviolet. If I go to tungsten, I got a lot of different shells. So depending on which shell I drop into the missing hole, I'll get photons of different energy. Since they're so big, I can get fairly big ones. Right? And we're usually, when we're doing, say, X-rays, just to give you some scope, let's say like 80 or 120 kilovolts, kilo-electron volts. So not in just the teens range, we're now in the thousands range. Thousands to hundreds of thousands. So I should say really tens of thousands to hundreds of thousands is typical range for an X-ray. So it's fairly significantly more energy involved in these. Right? But so now I get this really high energy photon coming, and it's coming at you, or coming at the thing I want to image. What does it do? How do I get an image from that?
Well, different materials in the body absorb the radiation. Right?
So this is understanding what it does, right? So we have to emit this. And then what we're going to see is who absorbs, right? We're going to see on the far side how many of these photons make it through and in what area. So it's kind of a statistical thing, right? There's no guarantee, right? I can shoot one and then shoot another one in the same direction, and they're not guaranteed they'll both get absorbed. So now I have to get enough that I can do statistics on this, right? So we call this binning, right? So maybe I'll shoot 1,000 in a particular direction, and I'll see, whatever 314 made it through, the other ones were absorbed. Right? So that tells me there's an awful lot absorbed. So either there was a lot of material, or it was a very high absorption material. Right? But that's what this is why they say it's a negative of what you're measuring, because it doesn't image what's there, it images what gets absorbed. Right? So that's why it's innately, in some sense, a negative. And we have to flip it to get what you want.
Okay.
Right? Less that makes it through means there was more or denser stuff there. So in that sense, it's kind of the opposite of what you would think the scale. That's why I say it's kind of an inverted scale. Right? Normally you think, I see more, that means more. But more means less.
Yeah.
Yeah.
And less, means more.
Yeah.
because you're measuring what survived. Right. I just do a flat image, right? So I can either scan it or I can release a whole bunch at a different angle. Right. We make the assumption that the photon is going to travel in a straight path. Does that sound reasonable?
Sure.
We usually look at most light travels fairly straight. The reality is when it passes through your body, it can get deflected, it can hit atoms, there's a lot of weird stuff to do. So we're going to study what those are, because we're going to have to find out how do we remove those. Right? So for our assumptions here under CT and these, right? So it's on the ionizing side. And we're going to make a second assumption, it's straight line. All right, so we want straight line, and we measure the non-absorbed. And from that, we can figure it out. Now, that's what a basic X-ray does, and you get a picture. Right? So you're going to get a map of, the really dense stuff versus the not dense stuff. So it is measuring kind of dense and high atomic number. Now, the reason why I say high atomic number, remember that tungsten, it emits, it's got lots of different bands. If you have lots of bands, you can absorb photons. Easy. The more bands you have, the easier it is to have an electron with the right transition. If you don't have an electron that can make that transition, you cannot absorb that photon. So higher atomic number ones just have more options. Lower atomic number, less options. So they're not going to absorb as much stuff. Now you can take a chunk off it, absorb, and then re-emit a much higher value one. So there are some ways you can kind of degrade the signal. We'll talk about some of those, but for the most part, we're going to just say, hey, look, the denser, more high atomic number stuff is going to, essentially be found by this. What's the big difference between, like, say, your skin and your muscle? Is there a huge difference in the density of them?
No, I would say no. No.
Yeah, it's not very different. There's a little bit of a density, but it's not huge. How about in the minerals that are inside it, atomic number stuff? Is there a significant? No. So guess what? When you look at soft tissue, you're going to be able to distinguish it using this? No, because what does it image? It images high densities or very high atomic numbers. How about bone versus skin?
Yeah, very
There's a huge difference on that, right? You got a lot more dense minerals. It's denser. You've got, also higher atomic number of minerals in there. What about fillings or other additions inside the body? Yeah, that's huge, right? So what you're going to distinguish and what it's going to be useful for, right? X-rays are going to be great for finding broken bones. It's going to be great for any of that type of stuff. You will see some tissue outlines, right? There'll be a little bit of a difference between the heart and some of the surrounding tissue, right? Blood does have iron in it and things like that. So you'll see a little bit of that, but it's going to be fainter, right? So it's really good with distinguishing hard versus soft tissues, but not good at distinguishing soft tissues. Cancer is mostly really dense when it gets later stage. So X-ray will be able to distinguish late stage cancers. Right? Once the tumor becomes really dense, X-ray will pick it up. Since it's a straight line path, it's really simple to get an accurate image. That's the thing we really love about this. That straight line assumption means we can be exceedingly accurate. Right? Other modalities like MRI is going to have a lot of distortion to it. So, it can be off by several millimeters on where something's located. That's bad, right? But MRI is going to count the number of protons that's in something. And that's going to give us a really good tissue difference. differentiation.
Mhm.
All right, so each one has their own assumptions, but if you kind of figure X-ray, straight line path, and it's going to measure these dense high atomic number, you'll get exactly what it's good for. How do I go to a CT? What does a CT differ from an X-ray? Yeah, you get 3D volumes instead of just a picture. So what we're going to do basically is we're going to take pictures from different directions, right? So we've got a body in between, and we're going to take a picture. And then we're going to do the same thing from another direction, and we'll take a picture. And we'll take the same thing from another direction, and we'll get a picture. And then we're going to reverse that process, right? We'll smear them backwards. We'll take a whole ton of these and smear them, and we'll figure out what the 3D shape looked like. I gain a whole bunch of pictures and kind of project them back. You know, and you can kind of imagine if there's a dense thing that's, you know, here, it was straight line along that path. And if the dense thing on this one was over here, it had to be along that path. And if that same dense thing was here, you can kind of trace them and find out where they all kind of match up. And therefore, you can find the location of something. Right? And in some views, multiple things might line up. So I need a lot of different images to be able to get a good resolution for a bunch of structures within the body. But that's basically the idea. It's a bunch of 2D pictures, and that's something, when we go to 2 to 3D, that technique will be a very common technique to use. Right? We'll get 2D pictures and we'll just combine them. So we'll do that for X-rays. We'll take a look. PCT, which I work on, very similar. Instead of using photons, we take the ion. Right? So it's, you know, we'll take that proton itself. We'll accelerate it to ridiculously high speeds. So instead of electron volts, we're going to go up to millions of electron volts. And then we'll shoot it at you, which sounds scary. But think about this. If I'm trying to shoot a really tiny thing like a proton at you, to a proton, what do you look like? Right? Pretty solid, right? Think you look solid to a proton?
No,
No, you're mostly empty
yeah,
space.
Yeah.
Right?
Yeah.
It's going to go right on through. There's not a lot there,
Uh-huh.
right? So from a proton's perspective, there's not much of you. Same thing to the photon's perspective, right? What it will do is there's all these electromagnetic fields connecting everything together, binding you up. Well, it's going to interact with those and slow down. The faster it's going, the less time it has to interact with it. So the more energy we give it, the less it interacts with you. So it's kind of an inverse to what most people think. The more energy I give the electron, the less it'll actually do to you. Because it's going to go so fast, it'll just go through, you won't even notice it. Right? But it loses energy. So instead of measuring who gets stopped, because pretty much all of ours are going to go through, we'll measure how much energy was lost. That'll say the electron field that it encountered. So it's going to be different than what an X-ray does. It'll measure Coulomb field. But high density, high atomic number stuff will have a bigger Coulombic field. But there's other things like water also has a good Coulombic field. So it'll give us, just like X-rays, but with the additional thing of it's going to give us some information around where water is. So we'll get, this will be similar to X-ray. We'll have less radiation because we're going to give it so much energy it'll just pass through, and nobody gets absorbed. Sorry about that. I've been talking so long and not drinking. Less radiation, so on the order of 1% the radiation, if you're wondering what it is. So ballpark about 1% the radiation to take in a 3D image as a CT will do. That's on. And a little bit of extra info around water. So it'll be like an X-ray with some extra water stuff. Now, where's most of your tissue comparative to water? Is it near water? Is it less than water? Is it more than water?
In terms of density?
In terms of density and its whole overall makeup.
Aside from bone, I feel like it'd be pretty similar to water.
Yeah, so all your soft tissue is very similar to water. We get extra information out of water.
So
So we
you
can
get
do
lot
a
of soft
little
tissue.
bit better job with soft tissue than X-ray can.
Okay.
Fine, and that's part of what the concern is for this. So this is one that's used, it's expensive, everything has a disadvantage, right? The difference is I need an accelerator. But you often use that to treat for cancer and things. So, you know, the advantage you're gonna get with a PCT situation is you'll get less radiation, so it won't interfere with the dosing the doctor wants to do. We can get a little bit more information, particularly around where the tumor versus cell differentiation. We'll be able to do a better job than they will in making that distinction. So it's useful for doing cancer treatments for radiation therapy, which will need that accelerator anyway. So we can image and treat on the same thing. So, but it's, other than that, it's gonna essentially be X-rays. Same exact math, you know, a lot of similarities that go on there. Make sense so far?
Yeah.
How about MRI? We've mentioned it briefly that it's really good with soft tissue, which the other stuff is. So why? Anybody know how MRI works?
It creates like a magnetic field, right?
It does, yeah, exactly. So what do I do with that? What does resonance tell you? If I said something resonates. Okay, so we're gonna polarize and we're gonna shake. So magnetic fields induce a moment on an electric field. So if you have anything like water that has an innate electric field to it, right, you put it in a magnetic field, they'll all line up and point in the same direction. And then I can use that field to move them between different positions, and they'll vibrate, they'll resonate. And you know, different ones will resonate because they'll have different moments compared to the mass of that molecule. So for instance, water will have a characteristic resonance and other stuff. So now I can tell the difference of exactly what you're made up with. As long as you have that polar moment, right? You respond to it. So only some bits of matter will. But thankfully, what mostly you're made up of does a really good job of resonating for us. So, you know, this will work great with hydrogens, it'll work great with water, it'll work, you know, a lot of stuff we really care about inside you are going to end up being nicely imaged, right? So that's what MRI is going to do. We basically cause these little resonances, and once we've got them resonating, then we'll measure the magnetic field, because as they're resonating, they'll disturb the magnetic field, and we can measure it at certain frequencies. So we're going to actually measure frequencies, right? And we'll tag different areas of your body with a phase shift. So every area in your body will impose slightly different field and phase to it, so we can measure back what the field and phase is so we can locate it in space. Right? And we do all these unique measurements at these different frequency and phase combos. What we're doing is actually rebuilding your frequency space. So we're going to be doing our measurements instead of in regular space. We're going to measure it in Fourier space. You reconstruct the image by doing an inverse Fourier transform. And you're literally done. So they're going to call it K space, but what they call K space is Fourier space. And all the work's going to be in how do we cleverly cause it to map out and read the Fourier or K space direction. But that's all MRI is, right? We have to be very precise to avoid things, so there's going to be lots of work on getting good magnets, and we want to get rid of noise, so we've got to super cool them, so like liquid hydrogen and stuff, you know, to keep them super cool so we remove noise, things of that sort. But MRI is all about, you know, causing those little vibrations inside the appropriate molecules. That make sense?
Yeah.
We'll go into the details, like I said. This is just an overview. So it's a little bit different in the way it's going to work, right? Field perturbation and measure how it, you know, how's it oscillate afterwards. How about ultrasound, real quick? What does ultrasound do? Do I have one probe? Do I have two? Like X-rays, I got an emitter and a
It's like
detector,
two, right?
right? Where's the other one, right? You always see the probe. Right, somebody holds in their hand.
Doesn't it come back?
It comes back and reflects. So instead of what we've been doing so far, it's been transmission. Everything in ultrasound is reflection. It emits sound, it bounces off something, it comes back. And we can measure the timing and how strong is the reflection. And, we can then figure out how deep things are, based on those. And we can reconstruct the image by the reflection. Essentially the same thing people do when they look into the ground with seismographs.
Is sonar similar to?
Exactly.
Okay.
So all of these are the same thing. So when you understand how an ultrasound works, you could help the Navy improve sonar on ships. You could help oil companies look for oil because that's all they do. They basically make a really big ultrasound. So they have like a vibra-sized truck that'll vibrate the ground and they'll measure back the reflected waves that come back. So all basically the same idea of ultrasound. Vibration, measure the results. PET and SPECT are another completely different thing. We're almost out of time, so I'll just give you a quick overview of the idea of PET and SPECT. These ones are neat because they're very useful. Let me do PET, which is the simplest one, but SPECT is a similar idea. Imagine I took a body, and inside that body I've got lots of little cells all around, right? And those cells have different metabolic rates depending on what type of cell they are, how active, what are they doing, things of that sort. So imagine I was looking for something with a really crazy high metabolic rate, like cancer. That means they're going to want a lot of energy. So they're going to absorb a lot of sugar. So I can take glucose, and I can give the body glucose with radioactive elements attached to it. Now this probably sounds crazy, but this is actually what we do. Right? So we take sugar, we attach a radioactive element to it, and we inject it into the person's blood. The cells with higher metabolism are going to take up a disproportionate amount of that glucose because they have a really high metabolism. That radioactive isotope is going to decay and emit radiation. So what's going to happen, like let's say this cell was cancerous right here. Right, so here's my bad guy, right? It's going to have a whole bunch of these. So with high likelihood, somewhere along the line here, it's going to absorb one of these, and we're going to get a decay, and it'll cause a little positron to go out, which will combine off, and then it will emit gamma rays, and they go in opposite directions. Right? And it'll go out, and we will have a ring placed around this. Right? So this is kind of my absorption ring. And it's all along here I have different sensors. And they're going to measure both that they got a hit and when. Right? So we'll get two stamps. If it was in the dead center, it would take equal time to get to both sides. Right? So the two time stamps would be similar. The difference between them tells you the offset along the line. They go in opposite directions, so all you have to do is take the two sensors' location and draw a line between them. That's the line it was emitted along. And the proportion between the timing tells you how far down. And we just get lots of these. Now, if I gave you a whole ton of radiation, I could get a really beautiful image. But then you'd have a ton of radiation in you.
Yeah.
Right? So now we want to say what's the smallest amount of radiation that I can reconstruct the important bits of information. So we're going to want, since we want really crazy low amounts of this, noise is really going to matter. We're not going to want to do a regular reconstruction. We're going to use some statistical ones to try to improve things drastically. Right? So that's going to be kind of our goal on this one. But that's basically the technique. Right? And instead of glucose, you could tag it on all kinds of different molecules. Like if I wanted to find COVID, I could get those little protein ones that are going to attach, to, and then I tag a radioisotope on those. So I can literally put my radioisotopes on anything I care about as a molecule and rate them off. And PET will allow me to then find out where those are. So it's a really good way. And since I'm going to tune this for crazy low values, because I want very low radiation doses in you, I can find even tiny, tiny amounts of something. So this is a a good technique for it. Now, of course, you're drinking some nasty radioactive goop or having radioactive stuff injected into your blood. Never our first choice of things. But if it's a difference between we can find some small amount of cancer and save your life versus not save your life, you'll take it. Right? Because it's often one of the more sensitive ones that's out there because we are literally doing one thing at a time. So PET is positron emission tomography. Right? So you get that little positron, it gives you the gamma rays from it. SPECT is single photon emission CT. So it does a single photon at a time. So, but a similar type of an idea instead of a dual pair. Anyway, so that's another whole one. It's usually used for that locating little tiny stuff. So those are kind of the big ones. We are going to go through, we will do X-ray first. Right? Then we'll talk about how we can adapt it to PCP just because I like it. We'll talk about MRI. We'll do MRI last actually. MRI will be last, ultrasound second to last. We'll do PET SPECT after we do the X-ray stuff. So those are the basic ones we're going to concentrate on. And then whatever we decide to do for a paper. For research class. But that'll give you enough areas that all the other techniques are just going to be that applied in a different way. So you'll have all the basics for them. All right, any questions? Cool deal. Well, awesome. This will give us, I'll upload the video as soon as I get access to it. It normally takes, it's been varies, depends on how many people are recording.